Hi there, Serdar Yegalop here for InfoWorld. In this episode of Smart Go, I'm going to take a look at GORM, an ORM, or Object Relation Mapping package for Go. An ORM is a way to work with databases that doesn't involve writing queries by hand. You use native metaphors in whatever language you're writing in to describe the data that you want to store and how to work with that data. GORM is one of a number of ORMs for Go, but it stands out for a couple of reasons. One, it's compatible with a wide variety of common databases, and two, it's very easy to set up and get running. In this example, I'm going to use GORM to work with a local SQLite database. GORM also works with MySQL, PostgreSQL, and a number of other popular databases, but we'll be using SQLite for this demo because it's convenient and fast enough for our use. The first thing we do with a GORM-powered database is create a model for the data, how we want to represent the database's data in Go. So for that, we create a struct, and the first field of that struct is going to be the gorm.model object. We then add other fields, like string for freeform text, or unsigned int for numbers. We can also use tags on these fields to tell GORM how to handle them. For instance, the name field here has the unique index constraint on it, and the year field is non-nullable. So when we create a record, that means that the name field will be indexed in such a way that there can be no duplicates in that particular table, and the year field must be provided. Now, each database has its own peculiar way of handling these things. So one of the reasons you would use something like GORM is to abstract away all the database-specific details about how to do that. Also, one of the other things GORM does for you is automatically add elements common to most database tables, such as an ID column, and also timestamps for when rows are created, updated, or deleted. These are all implicit in the gorm.model struct, but you can opt out or rename those fields if you need to. For this exercise, though, we're going to leave them in because they are useful. Next, we come to the body of the program, where we initialize the database and create the tables inside it, and that's done through these commands: gorm.open, which returns a database object, db, and db.automigrate, where we pass in the structures that we want to either initialize or migrate from an earlier version of the same database. Now let's create some actual data. To do this, we create an instance of the movie struct, we populate its fields, and we pass that to the db.create method. Now we've created 3 movies here, but there's a couple of things wrong with them. The second movie doesn't have the correct year, and the third movie doesn't even exist at all. We're going to do something about each of these things in a little bit. Next, we perform a query. We create an empty instance of movie to receive the data for the query, and we use db.first to get the first row in that table, ordered by ID. If we were performing a query that returned multiple rows, by the way, we would use a slice of instances of movie. But what would be more useful is to perform an actual query, to do more than just retrieve the first records that are available. And that's what this next section here is for. So we clear out the contents of the movie variable, and we use db.where to construct a query. And in this query, we're going to look for something where the field name matches Blade Runner. And so we use this syntax. We use the where clause, as it might appear in a conventional SQL query, and we use a question mark for a data placeholder. And then after that, the data that we will provide for those placeholders. And so from that, we will get the first record returned, and then we will place that into the movie variable. Now you might be wondering, why did we clear out the movie variable before making another request? Well, one of the things about GORM that's worth knowing is that when you use a model-based struct as the receiver for a query, if you have any primary key data already in that struct, it will be used to construct the query when you make the query. So in this next example, I take the movie.id field, which is the primary key for this table, and I set it to 0 before using it to receive the next query. I could do this, or I could replace the struct with a completely new empty instance if I wanted to. Either way, I get the same results. I get a completely new query instead of one that may be based on the existing ID that is already lingering inside movie. So this is something you need to be aware of in GORM if you're reusing the same struct object to receive multiple queries. You can also explicitly use a struct for querying and another struct to receive the results of the query. So for instance, in this example, we zero out movie, which will receive the results of the query, and we use movie query to actually perform the query. Now, one of the other things that we're doing here is updating an existing row. We take our movie struct and we use its update method to change the year for Blade Runner 2049 to the correct year that the movie was released, 2017. And finally, we have a query where we search for a movie by its year, 2084. That brings us the bogus Blade Runner 2084 movie that we mentioned before, which doesn't exist. And we don't want that in our database, so we'll get rid of that. We're going to use the delete method to do that. And that brings me to an important thing to understand about deleting in Gorm. By default, Gorm performs what are called soft deletes. Remember earlier how I mentioned tables in Gorm automatically have timestamps for creating, updating, and deleting rows? Well, when you delete a row, the default behavior is not to erase the row from the database. Instead, it's to fill in the deleted timestamp to indicate when the row was deleted. Any queries performed on tables through Gorm will automatically leave out any rows that have been marked as deleted, any rows that have a deleted timestamp that's not null. This is a reflection of current best practices with databases. You want to mark things for deletion rather than hard delete them. This lets you roll back deletes if they're made by mistake, and it lets you perform hard deletes later on down the line, say after a number of days, when you've confirmed that everything that you have marked for deletion should in fact be removed. Now, if you do want to perform hard deletes, where rows are removed entirely, then you use a different command. You use db.unscoped.delete, as I have indicated here. Now, when we run this code, we're going to get output to the console for all our queries. When we query the first row in our movie tables, we get a row that has the ID 1. That's the first row that we inserted, the movie Blade Runner. When we query for that row by name, we get that row again. And next we query for a different movie, one with the wrong data, which we then update with the correct data and we requery. And then finally, we have our delete action. Now, Gorm also provides ways to perform lots of other common database query and update actions, but for the sake of brevity, I'm only going to look at one more of them, retrieving data from two tables that have a join. So here in this revised example, I have a movie table and a role table, the roles that are performed by actors in the movie. And I'm populating the first one with a row for a given movie, and then I add rows in the second table that link back to the first one, a one-to-many relationship, as this is called. So when I want to query the movie and get all of the related roles with it as well, we use Gorm's preload method to fetch the data from roles that would match what we would also find in movie. As an aside, again, when we retrieve multiple rows with a query, as we do here with movie.roles, they just show up as a slice of structs, and so we can iterate over them as we would any other slice, as we can see when we run this code and we generate the results in the console. So to sum up, Gorm provides us with programmatic ways to work with databases, as ORMs do generally. It uses Go's struct type as the basic way to describe database tables, and to provide a place to store returned query data. It also includes ways to express things that are specific to databases, but can be abstracted away through the ORM interface, such as how to do things like require that particular columns be populated in a row. So that's it for this video. If you like it, please leave a comment below, and don't forget to subscribe to the Tech Talk channel on YouTube. And for more Smart Go and more Dev with Serdar, be sure to follow me on Facebook, YouTube, and Infoworld.com.